So as promised, here is a video, a short video about vertical asymptotes. Actually, I'm going to make two. I'm going to make one short video about vertical asymptotes and one about horizontal asymptotes. And I'm just going to get to it quick. So the first thing I'm going to do is give an example that I have already set up on Desmos. So let me share the screen. Okay, so simple example, 3x plus 2 divided by x minus 3. How do I see if there's a vertical asymptote here? I graphed it. And actually, I graphed the vertical asymptote, and you can kind of visually see, but I want to show you how you would know if this were a problem. If I gave you this, you'd say, oh, the bottom function is 0 at x equals 3. If I plug in x equals 3 into f, what I get is 11 over 0. So the fact that I get a number that's not equal to 0 over 0, that tells me there's a vertical asymptote at x equals 3. Now, I don't know exactly what's going on, so I have to do a little bit more digging. So I can look at the graph, and I can see that on the right side of x equals 3, the graph is positive, goes off to positive infinity. And the way I know that, if I zoom in, once that graph starts going straight up like that, it's not going to turn around. So I know it's going up to plus infinity, and I know that on the other side of x equals 3, it's going down to minus infinity. So I'm going to go back and zoom in a little bit so we can see it better. Okay, you can see the graph. It takes a while for it to get there, but it eventually does. So again, if I want to know exactly what's going on, I can look at the graph, or I can plug in numbers. And I'm plugging in numbers a little bit bigger than 3 and a little bit less than 3. And I want to see what's going on. Notice that when I plug in numbers bigger than 3, I'm just approaching 3. 3.1, 3.001, 3.00001. Notice that my values, my y values, get really big pretty quickly. The closer I get to 3. That's why the graph goes straight up. Now, if I plug in numbers on the opposite side, the other side of x equals 3, but close, like 2.9, 2.999, and 2.99999, you can see I'm getting numbers which are very big in the negative direction. So basically that's it. I look at the function. I see there's a 0 in the bottom when I plug in x equals 3. I plug x equals 3 into the function. I should make that clear. Plug into f of x. I get 11 over 10. 3 times 3 plus 2 is 11. 3 minus 3 is 0. I know there's a vertical asymptote there, and then it's just a question of graphing it to see. Okay, so let's do another example. Here's an exception to the 0 in the denominator rule that I just articulated. The bottom function is x minus 2. When I plug in 2, I get a 0 there, but if I look, I don't get any asymptote at x equals 2. Here, we even zoom out just a little bit. It just looks like a straight line. So why is that? Well, if I factor the top, what happens is the x minus 2 terms cancel. So really, what this graph R is, it's really the graph of y equal x plus 5 in disguise. I'm going to graph that. I graphed it in orange, and so now you can see the graph of y equal x plus 5. I'll turn it off, and now you see the graph of Rx. It's indistinguishable. There is one very small difference, and I'm going to show you what happens at x equals 2. So I'm going to look at the graph R of x, and look what happens when I get to 2. Finally get to 2, undefined. So technically, 2 is not in the domain of R of x. When I look at y equal x plus 5, that doesn't happen. If I go to where x is equal to 2, I get the point that should be there, 2, 7. So the only difference between R of x and y equal x plus 5 is that R of x doesn't exist at x equal 2. Otherwise, it's the same as x plus 5. So how did I know that? I plugged in 0, x equals 2, and I got 0 over 0, and then I graphed the function. That's how I know. Now I'm going to do one more example of 0 over 0 to show you that doesn't always happen. So here's another function. If I plug in 2 again, you're going to see there is a vertical asymptote this time. And notice the only difference is the square term. And so why is there a vertical asymptote here? You can see it develop. At x equals 2, when there wasn't one before, well, the reason is when I factor things, I still have the x minus 2 term at the top, but it cancels out with one of the x minus 2's in the bottom. So I have really what p of x is x plus 5 over x minus 2. And I'm going to graph, and really that's what. So I'm going to graph this, And again, it's in blue. You don't see any change between x plus 5 over x minus 2 and p of x, which is in green, this larger one. So the only exception to that rule, the 0 over 0 rule, is if there's cancellation. So I'm going to stop the share and to summarize everything. So if I have a function r of x equals p of x, q of x, and if q of, let's say, a is equal to 0, and if when I plug in a into q, I get something like k over 0. Sorry, this isn't, I'm going to write bigger. Where k is not equal to 0, I have a vertical asymptote. At x equal a. Okay. Now, so my example here was the first one we did, which was, I can't remember. I got to go back and look. It was 3x plus 2 over x minus 3. My vertical asymptote was x equal 3. I plug it in. When I plug 3 into the function, I'm going to get 11 over 0. So I know there's a vertical asymptote at x equal 3. We saw that. So then here's another example. Again, the bottom is 0 at x equal 2. However, I plug in 2, and I see what I get when I do all the work is what I'm going to get. Sorry. This should be a 10 here. Okay. So that was the second example that I used, not 7. So when I plug in 2, I get 4 plus 6 minus 10 over 0. I get 0 over 0. So there may not be a vertical asymptote. I'm going to say VA. Well, how do I know? I look at R of x. I see if I can factor it. And it turns out I can factor into x minus 2, x plus 5. Those x minus 2's cancel. And then I don't have a vertical asymptote. Really what happens is R of x is equal to x plus 5, except at x equal 2. Remember here it causes division by 0, where R of x does not exist. Okay. And then I'm going to do the last example, and that will be it. So again, here's the exception to 0 over 0. Not exception, but 0 over 0 could be a vertical asymptote. So my example was pretty much just a variant over that function that I had before. Except I have a square term in the bottom. I plugged in r equal 2. I see that the bottom is 0 at x equal 2. So I plug in my 2, and what I get on the top, I'm still going to get 10. 4 plus 6 minus 10 over 0. So I still get 0 over 0, and it really doesn't exist at equal that. So I'm putting quotation marks there. So I factor, and I'm going to the top is going to factor into x minus 2, x plus 5. The bottom is x minus 2 times x minus 2. This cancels, and this r of x is equal to x plus 5 over x minus 2. I plug in 2. Again, because the bottom is 0 at x equal 2. I plug in 2, and I get 7 over 0. I have a vertical asymptote. Okay. So the bottom line, if you get k over 0, k not equal to 0, you have a vertical asymptote. If you get 0 over 0, factor, and then see what happens. It could still be a vertical asymptote, or it might not be. Okay, this is what I was trying to get across today. I was trying to want you to explore, and we were going to talk about this. It just didn't work. So chalk that up to experience. Okay. Okay, so thank you. Hopefully that will help you make sense of what happened today in class.